Thanks, Sriram. Good afternoon, everyone. So we have 4 talks today. We will start with Professor Clesse about primordial black holes in the early universe. So this talk was scheduled in the afternoon session, but now we are having in the evening session. So Professor Clesse, please do start. So I will give you. I don't know. Yeah, because after 40 minutes, I will just unmute myself and tell you that we are reaching. And please everyone, keep your microphone muted, and after the talk we'll have question answer session. That time you can raise your hand and I will try to go one after another. And in case you are having any problem, you can type your question in the chat. I will read there.
Manjari, just a suggestion. If someone has a brief question, very brief question, they can interrupt, raise their hand. And
yeah, it's something very important. And if you think that without that answer, probably you will not be able to understand, or maybe it is very relevant in that slide, then please go ahead. Okay, so let us start. Please, Professor Clesse.
Okay, thank you very much. It's a great pleasure to be there today. Good evening, everyone. First of all, I have to deeply apologize for having missed the morning session. It's entirely my fault. I just misunderstood the timing of my talk. And thank you very much for the organizers for having accepted to reschedule my talk now. And I hope that we'll enjoy it. So I'm going to talk about a very hot topic these times, which is primordial black holes. Could have formed black holes that could have formed in the very early universe compared to stellar black holes, for instance. I will try to address the most controversial aspects of primordial black holes. That means whether they could be or not the dark matter, whether they could be or not the black holes that have been seen in LIGO, Virgo, and gravitational wave observations. And also how naturally would it be possible to form primordial black holes in the very early universe. But I will start with the less controversial aspect, and the less controversial aspect is that it became in the last years a very hot topic. So if you look at the number of papers cited as a function of the dates, we are really in an exponential, and all started in the 70s with Hawking, Carr, and Chaplin, who first proposed primordial black holes. In fact, based maybe on an older idea by Zeldovich and Novikov. And then there were different regimes, let's say. First, with the rise of inflation, people started to consider primordial black holes and primordial black hole formation mechanism in the context of inflation. With machos, compact objects in galactic halo, that could have been discovered by the macho collaboration, but then other microlensing surveys considered that it's not the case, and so there was kind of a rise, and then not really increasing expectation about primordial black holes. But what makes all people very excited again is the first gravitational wave observations. And then all started again, and last year, for instance, there were something like 2,250 papers with PBH in the title, which is, for comparison, something like 10 times more than WIMPs. It's really amazing. And what is nice also is that not all the papers discuss about gravitational waves. There are many papers also on different possibilities for primordial black holes, that very, very small black holes, huge black holes, and so on. And so that, but gravitational waves have been the reason of this new excitement for black holes and for primordial black holes. Now, here is the outline of the talk. So I'm going now to try to address the most controversial aspects of black holes. So I will try to make kind of review, but at the same time, I will give my personal opinion on these controversial aspects. So first of all, how natural is it possible to form primordial black holes in the early universe? Then can primordial black holes be the dark matter, and especially stellar mass black holes, because those are the kind of black holes that we see in LIGO Virgo observations. And the critical question is how to distinguish stellar versus primordial black holes in these gravitational wave observations. So let's start with the primordial black hole formation. So the basic idea is that you need density fluctuations. And in the very early universe, after inflation during the radiation era, if you have quite large density fluctuations that exceed the threshold value of order 1, then this density fluctuation collapses gravitationally and form primordial black holes. And of course, if you take small size fluctuations, they will re-enter inside the horizon a bit earlier, and they will collapse earlier and from less massive black holes. And for large size fluctuations, they will collapse later and form more massive black holes. However, on cosmological scales, what we observe is not order 1 density fluctuations, it's more like 10 to minus 5 density fluctuations in the cosmic microwave background. This is the left part of this plot. So in order to form primordial black holes, you need to go a bit beyond the standard predictions of slow Hall inflation models. And you need something a bit special, because you need a kind of peak in the power spectrum, in the primordial power spectrum of density fluctuations. And if the peak is higher, you could get higher abundance of black holes. And if you change the position of the peak, you can change the mass of the black holes that you will get. The difficulty is not really to have the increase in the power spectrum, but to have a peak. So to have an increase and then decrease of the power spectrum. And this is the way, in fact, that I got interested in primordial black holes. That was before gravitational wave observations in 2015 and a bit before. And I was studying hybrid inflation, and we noticed that there were some regimes where we could get this kind of peak and obtain stellar mass black holes, for instance. But in all these kind of models where you have a modification of the power spectrum, you have a double fine-tuning problem. Because, and that's very bad, because for Gaussian perturbations, if you want to compute the density of the black holes that you will form in the early universe, you need to integrate a Gaussian above some threshold. And when you integrate a Gaussian above some threshold, you get a complementary error function. And this complementary error function is approximatively a decaying exponential. So that means that the density of black holes that you form in the universe is exponentially sensitive to the height of the peak that you get, and to the critical threshold, delta critical here, that will lead to the gravitational collapse into primordial black holes. So if you change a little bit the amplitude, you change by a lot the abundance. And so it's very difficult to get, for instance, like an abundance comparable to the one of dark matter. And so I can already give you my personal feeling about this problem. I think it's a very, very important problem. And this led us, again, with Juan Garcia, but also with Bernard Carr, to try to find some ways and new mechanism in order to solve this double fine-tuning problem, because you need to fine-tune the amplitude, you need to tune also the position of the peak in order to get stellar mass black holes. And we have proposed this idea that could be a new class of models where, in fact, you could still have the standard prediction of slow Hall inflation. So you would have a Gaussian slow Hall power spectrum on all scales, but then the Gaussianity is a little bit modified. So if you can get rare large fluctuations in the tail of the distribution, so you see here the Gaussian distribution, so you move your head and you see the other direction of the plot in some sense, the vertical direction. So Gaussian fluctuations are there at 10 to minus 5 level, but you could have a little peak very far away in the queue that could produce the black holes on all scales. And then it changes the problem, because you don't have anymore a problem of modifying your power spectrum on small scales, for instance. And we proposed an implementation of this scenario with a stochastic spectator field whose quantum fluctuations make it exploring different parts of its potential, and only in very, very precise parts of the potential, it is able to generate large curvature fluctuations. That means that you have only rare large fluctuations that are produced by this stochastic spectator field. So that's the very basic idea, and I will come back a bit later also on that. But now you could ask yourself also, why would you get stellar mass black holes? Whatever it's a non-Gaussian model or just a standard Power spectrum with a peak or yeah, whatever. And in fact, there is a reason to have stellar black holes. And this reason is the QCD transition. And in fact, this is an inevitable reason, let's say. Because we know the thermal history of the universe. We know that there is a change in the number of relativistic degrees of freedom at the time of the QCD transition, especially. And this change induces a slight change in the equation of state of the universe. And because the critical threshold for PBH formation is dependent on this equation of state, and that the PBH density is exponentially dependent on this critical threshold, you would have, in principle, you should have a boosted PBH formation at the time of the QCD transition. And at that time, the mass of the black holes that would form is around the solar mass scale. And so you naturally end up with this kind of distribution. The overall shape could change depending on your assumptions. For instance, here we consider nearly scale invariant Power spectrum with a spectral index of 0.97. But with an enhanced amplitude compared to CMB scales. What is important are the features that are superimposed, that are just standard physics. And you get a peak around the solar mass scale, but a second peak also around 30 solar mass scales, which can be very interesting for LIGO events. And then also two other bumps corresponding to the electroweak and the E plus E minus transition. Around like planetary mass black holes and intermediate mass or close to supermassive black holes. And this is quite generic. So the idea to use a QCD transition from primordial black holes was already there in the 1996, for instance, by Karsten Jedamzik and then collaborators. And these kind of features were first discovered by Barnes, Hinmarsh, Young, and Hawkins in 2018. And I think that this has been a revolution in the way we can think about the mass of the primordial black holes. So it's nice because it's inevitable. It naturally leads to stellar mass primordial black holes. Only this does not solve the fact that you need enhanced density pre-fluctuation. So you would need kind of modification of the Power spectrum or a spectator field or whatever. But naturally, you can get these features in the mass distribution. Then what is also really nice is that maybe, in fact, primordial black holes could not only explain the dark matter, but also the normal matter. And this we noticed it that by considering the PBH formation process, if it happens at the QCD transition, because in that case, in fact, you are getting locally the Sakharov's conditions that are required for an efficient electroweak baryogenesis. But in that case, you don't need like new interactions or exotic physics. You are using the only known interaction that is not included in the standard model, that is gravitation. And in fact, you can use the CNCP violation of the standard model. You take the baryon number of violation of the standard model, and you will get the Sphaleron transitions that are leading to electroweak baryogenesis when you get very high collisions at very high energies during the collapse process, because the particles are accelerated during the collapse process of the fluctuation above this TV collision, but only locally. And so you have a process that is out of thermal equilibrium. There is the collapse, and there could be also a shock wave expanding around each black hole that would form at the transition. And this way, you get a maximal local baryon asymmetry. So if you look at the ratio between the baryons and the photons, it's more larger than 1 locally. But when you do the average, because the black holes, if they are the dark matter, would have a density of the order of 10 to minus 9, this will be connected to the total baryon to photon ratio. And those two numbers are very close to each other. So it's observed to be 5 times 10 to minus 10. So it's very close to the beta of the black holes if they are in dark matter. And since not all the black holes and not all the density fluctuation and finally end up in the black holes, maybe you can also relate the omega dark matter and the omega baryons. So it's kind of very natural process. At the moment, it's still like an idea that is not explored in full details. But that means that you have a model that could resolve at the same time dark matter baryogenesis, the coincidence between dark matter and baryons, also the amplitude of the baryon to photon ratio in the universe with a unified scenario. But we need more details to study this scenario. For instance, is there really a shock wave? Is it possible to dilute this normal matter that is created around the black according to primordial black holes? Because now we have an idea why they could have stellar mass. We have an idea also why you could have the abundance in the form of dark matter and the connection also between baryons and dark matter. Then we can focus on astrophysical and cosmological limits and study the question whether those primordial black holes could or not be the dark matter in the universe. And to address this question, there is one ingredient that is sometimes missing in the analysis, and that is coming from the Poisson fluctuations in the PBH distribution. So when they form, it happens that they form a bit more close to each other. So you have Poisson fluctuations in their distribution, and this has impacts on their evolution. First of all, that means that you have a merging weight suppression of the binaries that could form directly in the very early universe. So when two black holes form very close to each other, they could directly form a binary and eventually merge within the age of the universe. But this rate is suppressed because you will have quickly the formation of clusters of black holes coming from these Poisson fluctuations, and that will disrupt most of the binaries that would have been formed very early. And so this introduced this suppression factor. It's like three orders of magnitude, so it's very important. And then when the clusters of black holes from the Poisson fluctuation form, that means that you change also observations. And Kashlinsky, for instance, in 2016, has claimed that this is exactly what you need to explain the spatial correlations that are observed in the infrared and X-ray backgrounds. You need typically high Z clusters of black holes, a little bit of formation of stars inside those clusters as well to produce the infrared background. And the black holes are accreting matter, and so they emit X-rays, and so you have these correlations that appear. That means also that that's coming from the Poisson fluctuation, because of what Poisson fluctuation, they change the power spectrum. Those corresponds to other cooperative fluctuations, and the modification is going like FPBH times MPBH, the mass of the black holes, and K cubed. And you have, in fact, a 100% probability of having inhomogeneities collapsing into this kind of clusters at Z larger than 20, which would produce halos of black holes up to 10 to 6 and 10 to 7 solar mass. So that means that all the cosmological fluctuations that you will get below those scales, they will collapse into black hole clusters. And then they would evolve, because these black hole clusters, you have regular interactions between the black holes. And that means that these clusters are dynamically heated in such a way that you end up only with these 10 to 6, 10 to 7 solar mass black holes that could correspond, in fact, to the ultra-faint dwarf galaxies that have been detected recently. And with primordial black holes, if they are the dark matter, that means that there is a minimum radius for these ultra-faint dwarf galaxies that is of the order of 10, 20 parsecs. And this is exactly what is observed for the critical radius of ultra-faint dwarf galaxies. Then that's also important because of this additional clustering compared to the standard cosmological history. You are boosting the merging weights of binaries that would form inside those clusters of black holes. And so that has important impact also for the LIGO Virgo merging weights. In fact, you end up with merging weights that are compatible with LIGO Virgo observations, both for those binaries, but also for these early binaries. And finally, this is very important in order to evade the most important limits on the solar mass scale that is coming from the microlensing observations. Because now, if the black holes are the dark matter, they are all regrouped, or almost all regrouped in this kind of clusters, 10 to 6, 10 to 7 solar mass clusters. That means that when you are looking at a star in the imaginary cloud, for instance, when you have a primordial black hole between you and the star and have a microlensing events, in fact, this black hole is coming from a cluster. And this cluster introduces a lensing of the star. That is, with a small telescope, you are not able to distinguish this lensing effect, but your star will not be anymore a point source, it will be an Einstein arc. And that means that the microlensing event, in fact, applies to a little part of the flux of the star, coming from a little part in this Einstein arc. And that means that for these clusters that are coming from Poisson fluctuation, in fact, you evade microlensing limits because microlensing survey look at order one microlensing effects and not at just tiny variations of the flux of the star. And I would say that all this is not just a few numbers put like this. You can run n-body simulations with primordial black holes, and this has been done, for instance, by Yassin Ali Haimout and his students Inman. And they have taken different masses and different FPBH fractions, and they look at the distribution in the universe at a redshift of 100. So all this is the same redshift, but you change the fraction of black holes. And so if you have no black holes, you have something very homogeneous, as expected. But at redshift of 100, if you take FPBH equal 1, or if you take 10 to minus 1, you can see that everything is already collapsed into structures, and in particularly inside these clusters of black holes, of halos of 10 to 6, 10 to solar mass. So it's important to remind that on small scales, primordial black hole dark matter is very different than a particle dark matter. On very large scales, it's just exactly the same, but on very small scales, it's completely different. And this has implications for 21 centimeter signal, for recombination, and so on. While nevertheless, most of the people, maybe they still consider stellar mass black holes as excluded by astrophysical and cosmological constraints. And here's why. It's because when you look at the different papers and different probes of primordial black holes, like black hole evaporation from Hawking radiation on the left-hand side. So this plot shows the limit on FPBH as a function of the mass in grams at the bottom and in solar mass at the top. You see that there is a gap in the asteroid mass region. But then you have, at smaller masses, you have the Hawking radiation, the evaporation limits. You have the microlensing limits in blue up to the solar mass scale. But as I said, they would be evaded for stellar mass black holes, for instance, because of these Poisson fluctuations. Then you have many constraints between 1 and 100 solar mass coming from LIGO Virgo, coming from CMB, coming from black hole accretion that change for instance, the CMB anisotropy, so that you have also dynamical effects. You have also an effect on the large-scale structures due to this Poisson fluctuation that I've just mentioned. And so it seems that the solar mass region, in fact, it's the worst place to have a model of primordial black holes. And so let's say the less controversial idea then is to think of asteroid mass black holes, for instance, and then you can propose a model even with these QCD effects and the imprints of the QCD on the mass function. So you could also maybe explain a little bit some of the black holes seen by LIGO Virgo and have a peak. And this is a model proposed by Tony Riotto last year with a broad mass function, but peaking on the asteroid mass scales. And what is nice is that if they are not the dark matter, you even get even stronger limit. And you can see, for instance, these papers. So in fact, you move these limits down. However, it's important to notice with this kind of plot that all the limits are very model dependent. They are dependent on the PBH clustering, on the PBH mass function, and many also other technical aspects. So having asteroid mass function free is fine, but in fact, you get a new fine tuning, for instance, because why would the black holes have this kind of mass? When you include Poisson clusterings, you could remove parts of the blue limits. And in fact, at the solar mass scale, you are just at the border of the limits, in fact. So you are still allowed if you remove these microlensing limits. Especially also because those gray lines from LIGO Virgo, they are less stringent because of this Poisson effect that I've mentioned on the merging waves. That has not been included in the collaboration papers. So that's finally only a point of view, because you can have a more positive point of view, and this is the one that I prefer. And this point of view is to not only consider the limits, but also consider the clues in observations. And so it's a question of point of view, whether you would like to find new ways to exclude primordial black holes to be the dark matter at different masses, or whether you say, okay, maybe they are the dark matter because we see the dark matter, and I would like to be sure if there are not observations that maybe support this idea. And in fact, they are. So first of all, of course, there is the dark matter. So we should not forget it. So so there is an indication in the universe that there's dark component that could be made of black holes, for instance. There is one short microlensing event shown by this HSC telescope that suggests that maybe there is something here. There are also observations of microlensing, and those two microlensing surveys are towards the galactic center, which is different than in the Magellan clouds, because you don't probe PBH clusters in the galactic center. They would have been disrupted. So you are probing just dark matter with some profile. And this suggests then something like 1% of the dark matter for Ogle microlensing is made of planetary mass black holes. You have also some quasar microlensing. This has been considered as a limit, but also there are a few cases where you see a microlensing event, but coming from a galaxy that is not aligned with the quasar, which means that you are probing the halo of the galaxy. And that means that you have something compact in the halo of the galaxy. This is an argument often claimed by Hawkins. You have also detection of microlensing events towards the galactic center, both with Ogle and Gaia, especially black holes in the low mass gap, where in principle, we didn't expect to see black holes. You have this critical radius of ultra-thin dwarf galaxy that I have mentioned. The Corpus problem could be also explained by barrel black holes due to their interactions, because then you end up with something like a self-interacting dark matter model because of the gravitational interaction. And strangely, the sigma over m for this self-interacting dark matter is of the order of 0.11 centimeter square per gram, which is the kind of value that you need in self-interacting dark matter to solve the Corpus problem, but with black holes and with gravity. Then you have LIGO-Virgo observations, both at 30 solar mass, but also some candidates also near the solar mass scale, where we don't see an electromagnetic counterpart. I will come back to that later. And gravitational wave background from pulsar timing arrays, because it's not yet sure that it's a background, maybe it's just noise, but that could be due either to black hole binaries or either to second order, to gravitational wave emitted at second order in the perturbation theory, but linked to the existence of these large density fluctuations in the very early universe. And finally, we still don't know the origin of the supermassive black holes at the center of galaxies. And basically, you could need this kind of seeds at large masses that could be coming from primordial black holes. And altogether, if you take the mass function that you get from the QCD transition, for instance, you can adjust a little bit your parameters to pass by all these clues. And so it's a radical, it's a completely different way to think of the problem. Look at the kind of observation that you could be explained by primordial black holes that could pass the limits if they are clustered and so on. And try to find a natural model to pass through these observations. But there are still also some problems. So how to avoid, for instance, a subasteroid mass range with where there are some limits also here, but maybe it's linked to the energy scale at which you start forming primordial black holes. Slight tension with seg1 limit around the solar mass scale, which is an ultra-faint dwarf galaxy. Also CMB limits, but the problem is that CMB limits have not yet included clustering that I've mentioned before. And so strictly speaking, they don't apply to the kind of model that I'm presenting here. And then CMB distortions as well that could make supermassive black hole seeds in the form of primordial black holes excluded, but only for Gaussian fluctuation. If you take a non-Gaussian model, the one that I've mentioned also at the beginning, then you could pass also this problem. Okay, in the last part of my talk, I'm going to talk about LIGO-Virgo observations now, and whether it's possible that some black holes detected so far are primordial or not. And first of all, let's consider the merging rate. So it's a slide that is a little bit more technical, but don't look at the details of this formula. This is now, let's say, the standard formula for those early primordial black hole binaries that would form in the early universe. The rates are in per gigaparsec cube per year. And for late binaries inside clusters. And in these two formulas, you have two parameters, F suppression here and R cluster here, that depends finally on the model that you will take. And you have the FPBH, and F of M is the mass function. So right after the PBH formation, there were three papers claiming that primordial black holes could or could not be the dark matter, but could explain LIGO-Virgo observation. So for early binaries, that was by Sasaki and others, they say, okay, no, you can only have 1% of the dark matter made of black hole because they took this formula, but they didn't consider the rate suppression that you can get due to Poisson fluctuation that have been put in evidence later using n-body simulations, for instance. And in fact, if you take this into account, you end up within the range of LIGO-Virgo, for instance, for solar mass black holes and FPBH equal 1. But there is also an issue with the rate of disrupted binaries. So maybe this kind of binaries, they can also be disrupted by cluster, but those one could still match. And so there is still some, maybe some problems here, but it's only one paper. And for monochromatic mass function, so it's not clear what happens for wide mass distributions, for instance. And then for late binaries, first proposal also in March 2016, when there were the two proposals here, by Burt et al., the famous did LIGO detect dark matter paper, they used the standard Hello mass function, so without including the Poisson clustering. And they use then R cluster between 1 and 10, which means that it's possible to have a PBH equal 1 for the 30 solar mass. But then it's in contradiction with the claim by Sasaki and others. However, in fact, we should have enhanced clustering because of the Poisson fluctuation if FPBH equal 1. And so if you take this into account, you boost the rates by something like 1 or 2 orders of magnitude, and you can still get today FPBH equal 1. You can get the rates observed at the solar mass scale, but only have a little fraction of the black hole in form of dark matter for the 30 solar mass black holes. And this is unavoidable, this clustering. See, if FPBH equal 1, this is unavoidable. And so we have computed, for instance, distribution of the merging weights. So you see, as a function of M1, M2, the rates for early and late binaries, including this clustering due to Poisson fluctuations and so on. And in fact, it's compatible with 3 of the most strange events that have been detected so far, like 1904-25, who didn't have any electromagnetic counterpart, and that is also the larger mass for a neutron star known so far, so it's a little bit strange as well. This one with a very low mass ratio, 1908-14, and this one with a black hole in the peri-instability mass gap, where in principle from stellar model you don't get black holes. And these 3 events are compatible with the kind of mass function that I have shown before. What is nice is that you are also consistent with the subsolar limits, but also you have some motivation to look for subsolar black holes in combination with a higher mass black hole, because the rate is higher for this kind of binaries. So in summary, regarding merging weights, early and late binaries, they compete at similar levels. It's difficult to say which one is the highest, due to this Poisson clustering that suppress the rate of early binaries and boost the rate of late binaries. What you can have is FPBH equal 1 at 2-3 solar mass, but probably less at 30 solar mass. It's more plausible, as expected for a QCD transition, by the way. This is where you would have your little peak coming from the pions that become non-relativistic. And at 2-3 solar mass, FPBH equal 1 is possible, both for early and late binaries, but you need to be careful and cautious with the rate of disrupted binaries, and maybe this needs further investigation. Then let's look at the strange mass of the black holes detected so far. So those are all the events that have been detected in the third, coming from the third catalog of LIGO Virgo. And they are strange black holes. They are strange measures. For instance, there is a series of black hole progenitors where at least one of the black hole have a mass that is likely in the peri-instability mass gap that starts above 60, 70 solar mass, and above which, in fact, supernova explosion are expected to leave no remnant at all, and so you would not see black holes above these masses for stellar models. But we see, in fact, some of them. And it goes up to 100 solar mass in the latest catalog, with 107 for this one. It's not a very, very clear detection, but so there are large uncertainties, but nevertheless, it's very strange that, so it seems that there is, in fact, a continuous transition in the mass function of the black holes going inside the mass gap. And so some people have claimed that maybe you can explain that with measures in dense environments, which, by the way, is the same as the idea of having primordial black hole clusters. It's also a very dense environment. But in the case of stellar black holes, Sorry?
So
I'm not
can
sure
there is background noise, please ignore it. Yeah.
Yeah. So well, I'm about at the end of my talk, so I'm going to conclude after this slide. So just to say that it's difficult to explain this kind of black holes with stellar black holes, because inside clusters they would get velocity kicks and so on, and also it's difficult to say why we would see, for instance, two black holes that would come from previous mergers and not only one, and that, on the contrary, is consistent with primordial black holes. You have black holes in the lower mass gap also, where we don't see the black holes with electromagnetic signals, and asymmetric black holes that are difficult. Yeah, it's very hard to make a stellar model compatible with the existence of this very asymmetric events. So I'm passing the spins of the black holes that are relatively low also, and the gravitational wave background, because it has not been detected so far. Just say that, in fact, for primordial black holes with wide mass distribution, we could just be at the limit of detecting it. So. And I will finish my presentation with subsolar black holes. That's clearly the best way to distinguish primordial and stellar black holes. And in this paper, we found 4 candidates in a reanalysis of the second run of LIGO Virgo. So we don't have yet the parameter estimations for this event, but let's say that the best template, they indicate that it could be subsolar black holes. And in particular, for 2 of them, those are 2 triggers event. The first 2 ones are only seen in 1 detector, and the other 2, they would be seen in the 2 detector. And so maybe it's just the beginning, and that we start finding subsolar primordial black holes. So stay tuned, because we are still analyzing O3 data and so on. And so let me conclude. In fact, primordial black hole, they have specific PBH mass and abundance that would require fine-tuning, but recently, some more natural scenarios have emerged, with, for instance, with the QC transition, with the idea of having baryogenesis linked to the primordial black holes, or to have non-Gaussian fluctuations. There are 2 ways to see astrophysical limits. Either you see some clues in observations, or either you see only the limits. And so that makes a very hot debate whether or not FPBH equal 1 is excluded or not. And I would say that, in fact, you can still have FPBH equal 1 at the solar mass scale when you take into account the fact that the black holes are in clusters due to the Poisson fluctuations. And finally, gravitational wave observations, the rate mass spins are very intriguing, but I would say not yet fully convincing. And so it's interesting because we have soon new observations to analyze and so on. And so that we'll be able to probe PBH models, for instance. Altogether, we have a very complex phenomenology, much more complicated than what people can naively think, for instance, on formation, clustering, accretion, mergers. And so really strong statements are still premature because they would be model dependent. But the common agreement is that finding a subsolar black hole is probably the best way to prove the existence of primordial black holes. 4 candidates have been found, but those are just candidates, not clear detections, of course. And so stay tuned, because we need to analyze them. We will have soon all the data, and so hopefully we will see them in the future. So thank you very much, and if you have questions, I will be happy to answer.
Thank you, Professor Clesse, for such an exciting talk. So we have time for 2-3 questions. So please. Okay, I see some hands raised. So
Kandu, I will help you, Manjari. Kandu, please unmute and speak. Ask a question.
Thanks a lot. You can hear me, hopefully, yes.
We can.
Yes.
Yeah, it was a very interesting talk where you tried to form things during the QCD phase transitions. So I had a couple of things. One is, you said these guys cluster, so they may not cluster during the radiation-dominated era, right? I mean,
No, well, they start, in fact, they start to form clusters during the radiation era, but it's a slow process.
there can't be rapid growth of structures at that era. I mean, it can at the most be logarithmic or something.
No,
like
but they are very small clusters. Huh? So the ones that are going inside the radiation era.
The second thing is, there are these pictures which you showed of something expanding out. I mean, so the collapse also was also leading to an expanding shock.
Yeah.
But then you indicated some horizon which is smaller than this radius of the shock. So I'm a bit confused what's happening here.
Sorry, ask again.
So there is a horizon, Hubble horizon, which is smaller than the radius of the shock.
No. It's well, the point is that you have a density fluctuation that is originally of the order of 10 kilometers at the QCD transition, and this one can collapse. And right after the collapse, you can have also a shock wave that expands because you have this acceleration of all the particles, and so not all of them end up in the black hole, and some are expelled away inside the shock wave. And this is the way you can get the high energy collisions with the very dense environment that is outside the black hole. And so then when the shock wave happens, the Hubble horizon has growth, of course. Huh? So the 10 kilometers is the Hubble horizon at the time of the start of the process.
Okay, then it becomes bigger.
Yeah.
Then does this shock then lead to also turbulence and gravitational wave production?
Yeah, that's a very interesting aspect, and I'm not sure that it's the case. Maybe it can produce this kind of gravitational waves because you have other black holes nearby. And so all process, even if it's spherically symmetric, even if the black hole formation and the shock wave is spherically symmetric, because the primordial black holes will have no spin, for instance, maybe if you consider then the interaction between different shock waves
yes, that's what
produced by the different black holes, maybe this could lead to gravitational waves, yes. But this has not been studied so far, and I would say that even the shock wave, it's still a little bit hypothetical because it's not sure that we see it in the simulations in numerical relativity of formation of the black hole. So some of the simulations show something like a shock wave, and some not, and it's not. For me, it's not so clear that there will be a shock wave. It could make sense, but we need more careful investigation.
I mean, that's how supernovae are formed. So it's similar.
Yeah, it's a kind of primordial supernovae, in fact. Yeah,
okay,
exactly.
I will probably ask later anything else.
Yeah, I think so. We don't have much time. So, hi, Raghavendra, is your question very short? So maybe
Yes,
we can take that. Yeah.
Quick question. The parameter that you introduced, Professor Clesse, in your slide 9, F suppression, you quoted a number of around 2 into 10 power minus 4 or something. I just wanted to know how it is motivated. Is there an analytical estimate, or is it derived from simulations or something?
Yeah, there is an analytical estimation that has been confronted to n-body simulations. And so there is an analytical formula that you can look in paper by Marty Rydal. And there is another one also from 2020, where it's a little bit more precise. And when you take FPPH equal 1, then you get this suppression factor that is 2 times 10 to minus 3. Yeah.
Okay, this is effectively capturing the clustering effect, I believe.
Yeah, exactly.
Okay.
Yeah.
Thanks.
Manjari, I think we can request Rajiv to ask the question since he had raised his hand, and then Rajiv, a brief question.
Yeah.
Hi, Sebestien. Hi, this is Rajiv.
Hello.
Hi. So I had actually a comment on the very last point on your very last slide. And you mentioned that if the detected PBH are subsolar, they have to be primordial. I think spin also plays an equally important role, is that if they are detected with almost a negligible spin, then we can say even with much more sort of confidence that they have to be primordial. Because the astrophysical black holes must necessarily possess a spin, and the ones without a spin can only be primordial. Is that correct?
Yeah, I think that's correct. Well, for me, I would say that the difficult part will be to distinguish them from neutron stars. And neutron stars have low spins. And so in that case, maybe it's not so an argument, let's say.
Okay, I understand.
But if you think, even if you think, for instance, of some proposals that have been proposed, that have been put quite recently, that subsolar black holes could form also from dark matter. And in this kind of models, usually the spin of the black hole is not 0, and it's more like 0.7 or something like that. And so this could be a way to distinguish this kind of dark black holes from primordial black holes.
I see. Thanks. And my second quick question was that in one of your plots where you were showing the fraction of PBH in terms of dark matter as a function of mass, in the very, very high mass range, you were showing yet another region, this one, which also is unbounded or unconstrained.
Yeah.
Okay. Can you comment quickly about where does this come from? Because this is the plot I'm seeing for the first time in this such a massive domain.
Well, it comes from this review by Karen Kuhnel. And in fact, they point this region also because, they have, I think it's both of them, they have a paper on stupendously large black holes, where they claim that in fact, it could be possible that black holes with a mass that is even larger than the galaxy cluster, some of these black holes could exist in the universe. Of course, they could not be the dark matter because you see also the dark matter locally. But strictly speaking, you don't have a limit on that region. Well, except the fact that, of course, you see the dark matter locally. But if you think of 10 to minus 2, for instance, you could have maybe 10 to minus 1, 10 to minus 2 of the dark matter made of these very, very, very huge black holes.
I see. Okay. Yeah. Thanks a lot.
There is only one paper on that.
Okay.
by
means,
Kuhnel, also.
Yeah, something to look at. Okay. Thanks a lot, Sebestien.
Thanks, Professor Clesse. Thanks for exciting talk, and thanks everyone for interesting question and answer sessions.